random functions is, that part is maybe the most abstract part of this lecture series. But it's important because it's basically the theory underlying geostatistics, time series analysis, Kalman filtering, and any of those stochastic methods that we explain later on in this lecture series. So up to now we've been looking at the modeling the unknown value of a single value without considering the locations or the coordinates of that value. For instance, hydraulic conductivity at a certain from a certain aquifer without considering the exact location where the sample was taken can be modeled by a random variable. And the random variable concept imagines that a unknown value is an outcome of drawing from a probability distribution. So that's generated by some random process. The underlying random process is described by a probability distribution that tells us in advance not what the exact value is going to be of a certain draw or realization, but what the probability is that a certain range of values or a certain value occurs. One step further is if we are interested in the unknown variation of a variable, either in time, space, or space-time. So we have something that is random. We don't know the outcome in advance, but we also assign it to a certain location. So this may be hydraulic conductivity at a certain location, the discharge of a river at a certain time, or something that is even in space-time. So a groundwater level occurring at a certain location at a certain time. And that is described by a random function. So this whole lecture is about the concept of a random function and its properties. So some examples of, this is a time series, for instance, of the Meuse discharge that we used in the practical. This, as you can see, it maps the occurrence of a certain discharge at a certain time. So this can be described by a so-called time random function. And a time random function is often also called a random process or stochastic process. Then it can also be in space. This is an example of a data set collected by the group of Roger Grayson in the Tarawara catchment in Australia, where they mapped using a TDR on hydraulic rods on a small vehicle, map out, taking thousands of samples to map out the spatial variation of soil moisture content. And you can see it has some structure, but also some apparent noisiness, randomness. And this can also be described by a so-called space random function. And that's often called also a random field, if it's in 2 dimensions. And then finally, he did this for multiple times. You see how the soil moisture changes over time. The red and fiery purple colors are very low soil moistures, and the dark blue are the highest soil moistures. And obviously, this can be seen as an outcome of a space-time random function. So it has 2 spatial coordinates and a temporal coordinate. Now, what's the concept of a random function? Well, a random function can be seen as a realization of functions in time, space, or space-time that all have the same probability of occurring. So it's a random draw from a collection of functions. All the possible functions together is called the ensemble. And you see 4 members of this ensemble here. And one particular member or draw or sample of all of the ensemble is called a realization. Some people also call it a sample. You can imagine that you have an infinite number of those functions and you put them in a big bag and you just randomly draw out functions. And these functions are not, they are the same, they are of course not the same, but they are more or less similar in the sense that they have the same statistical properties. They may, for instance, have the same mean or the same variance or the same correlation structure in time or space. Yeah. So they have the same statistical properties, but they are not, of course, exactly the same. Now, we can play around with this R package called simultimeseries.r that draws random functions or realizations from a time random function or random process. Let me show you that, and then I can go to R, for instance, and then run this, and you can actually see here I can resample. So these things all have the same variance and the same mean. So if I change the mean, you can see that you can see the y-axis changing. So putting the mean back to 0 here. I can also change the variance. You can see that the variation changes. And I also can change, and we'll come back to that later, the correlation structure. So this is the correlation. The larger theta, the more correlated the thing is in time, and you see that there's much more structure there. And if it's very small, then it's almost white noise. Yeah. So this is a so-called time random function, realizations. So I can resample and get another realization of the same random function. Yeah. I can do the same in 2 dimension. Then I get a random field. This is a random field that has a Gaussian distribution. Of course, I can change the mean. And again here, I can try to resample. Resample. I get the different realizations, but they all have the same statistical properties, but they're just not the same. Yeah. So that's the idea behind a random function. So this is a time series realization, and you know, if you draw a new sample, it's just like you know, in our first lecture, shooting the error with some random noise on it. It's just by drawing a random variable, but now you're not drawing a random variable, but you're drawing complete function. Yeah. The same with space. You're now drawing a complete 2-dimensional spatial function. And that's the same as putting all the possible 2-dimensional functions in a big bag and then randomly drawing realizations from them. Now you can also draw multiple realizations, obviously, of that. That can be seen if you go back to our R package, and we go, for instance, back to the time series one. Let's rerun it again to get. We can also increase the ensemble size. As you can see, let's increase theta a little bit so that we can see a little bit more structure. So you see, these are all here. I have 5 different realizations of the same underlying random function. So what you see is that this can help us describe basically what if we have something that is varying in space-time or space-time, and we want to represent our uncertainty about this variation, we can draw these alternative realizations and giving us basically a full spatial or temporal distribution of our uncertainty of time or space-time. Now, like I said, you can have random functions can be a function of time, space, or space-time. If it's a random function of time, it's often called. Let me get the pen out. It's often called a random process or stochastic process. If it's a function of space, it's often called a random field in the literature. And if it's a function of space and time, note that I just for a shorthand, writing it shorthand, I denoted the spatial coordinates as a vector, 2 or 3-dimensional vector, depending on whether you are considering 2 or 3-dimensional space. And a this is often called a space-time random field or a random space-time function. Right. Now, this is one way of looking at a random function. So we have an infinite number of underlying functions with equal probability of being drawn, and we can each individual draw or sample is called the realization, and all the realizations together are called the ensemble. But another way of viewing it is as a collection of random variables, one at every time or every location, that are mutually statistically dependent. So we may have a random variable at T1, and we have a random variable at T2, and that random variable has the samples of that random variable are just the values of the realizations of the different realizations across the ensemble. So here we see, 6 different realizations, or 7 different realizations, and this is a probability density telling you something about the random variable z at T1. Similarly, we can also have the random variable at T2, and that can have a totally different probability density. Yeah? So it doesn't have to be the same. Mm-hmm. So at every location we have a probability density function that describes the uncertainty of the random function at that particular time coordinate. So that's another way. So we can look at it as a collection of those functions, we see here, but we can also look at it as a collection of random variables defined at every time coordinate, and they are mutually, of course, dependent. We will see later, because of the continuity of these functions, you can imagine that if you find a low value at T1, likely is that you also find a low value of the same realization at T2. Now, because we can see it as a collection of random variables that are a function of space-time or space-time, we also have that the mean, that the probability density function is a function of time, space, or space-time, and obvious therefore also the mean and the variance are a function of time or space-time. Yeah. So in this case we can see that the mean of z at location t is the expected value of z at location t, and we calculate it by integrating z times the probability density of z, yeah, which is a function of time as well. So the probability becomes a function of time, and therefore the mean is also a function of time. And we can also calculate the variance from the probability density function according to this equation. Now, I said they are mutually dependent random variables, and that's the case, of course, because if we take T1 and T2 close together and we plot the value at T1 and at T2 for the same realization, yeah, so this is T1 versus T2, we can see that they are quite on a one-to-one, not a one-to-one line, but they are basically positively correlated in this case. This is likely because the continuity of these functions means that if we look at the realization of the random variable at T2 and it's close to T1, it's likely to have similar values, right? So this is why they are positively correlated in this case. And if you look at the bivariate probability density function, and suppose it was Gaussian, it looks like this. Now, if we take a location T2, which is much further away, then of course it's likely that this correlation diminishes, this dependency. And you can see that by taking T2 farther away. You can see when you get farther away, then there's actually they all plot like they're not plotting on a line anymore, and you can see that the bivariate probability density function shows that there's actually no dependency anymore between T1 and T2. It also shows you that there's a certain time length, or in space length, that random variables are still dependent, and if they are further apart, they become independent of each other. Now, this dependency, like I said, can be described by a bivariate probability density function. So instead of describing the bivariate probability, the joint probability of, say, Z and Y, Z being hydraulic conductivity and Y porosity, this describes the probability that the discharge, for instance, at T1 is between certain intervals, and the discharge at T2 is between certain values. Yeah, and of course, if we make these intervals small enough and we take the limit, it becomes a bivariate probability density function. And you can see it's a function not only of the value of Z1 and Z2 itself, but also where it's taken. Yeah, where Z1 is located in time and where Z2 is located in time. And then from the bivariate probability density, we can also calculate the covariance, taking the expected value of Z minus its mean at T1. Z, so this may be the discharge at T1 or the groundwater table measured at T1. This is maybe the groundwater table measured at T2. And this is minus the mean, which can also be different depending on where you are in time. And by definition, it can be calculated from the bivariate probability density function as such. Yeah. Now, the bivariate probability density function tells you how what the joint probability is of two variables. But of course, if we are thinking, for instance, at a random function of time, we can try to say something about the dependency structure of variables at 3 time steps, or 4 or 5 or even 10 time steps, or 100 time steps together, and that's called the multivariate probability distribution of or probability density function of a random function. Yeah. So the multivariate probability. So it tells you the joint probability that at n locations, n can be any size, can be 1, 2, 3 until infinity, what the probability is that, what the probability density is that at these instances in time, certain values of Z1 to Zn occur. Yeah. So if you want to jointly know what is the probability that the hydraulic the discharge at at day 1 is larger than 10 cubic meters per second, at day 2 smaller than 2, and at the same time day 3 larger than 20 and day 4 larger than 50. This joint probability can be calculated if we know the multivariate probability density function. It's often also called multi-point PDF because these variables are actually the same type of variable but measured at different places in time or space, right? So this is often why they call this also called the multi-point probability density function. Now, what you have to remember is, if we know for any set of points n, if we can somehow calculate the multivariate probability density for that number of points, we know everything there is to know about this random function. It completely defines the statistical structure of the random function if we have the multivariate probability density for any set of points. Yeah, that's important to remember, and we will get back to this after the break. Okay, so this is everything we need to know about a random function is encoded in its multivariate probability density function. Now let's go back to what type of random functions do we see in practice? Well, actually, we can make a classification of type of random functions in the literature based on the value. So they can either be discrete and they can be continuous. Well, we already looked at continuous. Think about discharge over time. But you can also think of discrete, for instance, a certain counting process. You can think of, for instance, what is the number of rainstorms that occur on a given day in a certain area. Yeah, that's a discrete number. Yeah, or it can be a 0 or 1 variable. You can be above a certain threshold or below a certain threshold. Yeah, so those are discrete valued random functions. Then we already saw that we can have different domains. It can be a function of time, space, or space-time. But the way those domains are defined can also differ. For instance, it can be continuous in x and t, so any value or any coordinate in space or time is possible. But sometimes it's more convenient, especially in time, for instance. Suppose you measure, you gauge rainfall, and you only do it every morning at 7 o'clock. You empty the rain gauge, so you have discrete times at which you measure your accumulated rainfall for the previous day. Then it may be more convenient to only take a number of discrete points in time. Yeah, so it can be discrete in time. Similar in space. If you do grid sampling, you only sample, or you have, for instance, a groundwater model where you're only looking at the groundwater level at the center of a grid node from some discrete groundwater, some mod flow model, for instance, that describes groundwater flow, then you have a discrete number of points. Yeah. And these points can also be random in space and time. I will come back to that actually to explain this one. That's a weird one in the next slide. So the next slide shows you some examples of random functions. So these are 4 realizations of 4 types of random functions. They're all continuous, as you can see, they're all continuously valued, as you can see. So they all belong to this. So they can get any value of z, but here you can see it's continuous in time. Think about measuring discharge with a pressure or water levels with a pressure transducer that continuously measured, or it can be discrete in time. Think about reading a rain gauge, manual rain gauge every day. Yeah, so you have a different value that can be any value of z, but you have it at discrete time steps. This is also called a time series model, and we use that in chapter 6 is about time series modeling. Yeah. There's a special set of techniques that we can apply if we have this discrete, continuous valued but discrete in time random functions. Then this is what you can see is where we have z, but it's only defined at a grid, and often what they do is this is described as a continuous process, but then only sampled at discrete locations. That's one way of doing it, but you can also, from the get-go, see it as a discrete space, continuously valued but discrete space process, also called a lattice process. And then finally, this is a continuously valued process, but you can see it's only defined at random instances in time. And you can think about this is another word of such a random function is called a so-called point process. So you have 2 sources of randomness: the occurrence of the event, so they're occurring randomly in time, and when the event occurs, there is a certain random value attached to it. Think of, for instance, these are very intense rainstorms that occur on random times, and attached to each rainstorm is the total amount of water that is dropped. You know, the rainfall intensity that is attached to each rainstorm. Yeah. So that is actually a special type of random function called the point process. And they are also, you can also think of rainstorms in space or space and time occurring with a certain dimension, for instance, that can be a random, and an intensity that can be random. So you can see there is a plethora of different type of random functions depending on whether the value is discrete or continuous, what the domain type is, and how the domain is defined.